dynamic programming. This time I'm going to be talking about both dependency parsing and phrase structure parsing. So the reading material only covered dependency parsing, and it didn't really cover any neural methods, except for a brief mention. So I think most of the material here should be new. As I've noted before, there's two types of linguistic structure. We have dependency that looks like this, and phrase structure that looks like this. Dependency focusing on the relationship between the words, and phrase structure focusing on the structure of the sentence. And parsing is predicting linguistic structure with transition-based models, which we talked about last time. And this time I'm going to talk about dynamic programming-based models. So kind of the important dichotomy here is that the transition-based models are like the history-based models for part-of-speech tagging that make individual local decisions and then make their next decision based on their previous decision, while dynamic programming-based models do some sort of dynamic program to find a globally optimal solution. So that was also the first quiz question. And this is like the linear CRF for part-of-speech tagging. So the first one is minimum spanning tree parsing models. So if we're talking about graph-based dependency parsing, this was also in the reading, but basically we express a sentence as a fully connected directed graph that looks like this. We score each edge independently. So each edge gets a weight that corresponds to this. And then we find the maximum spanning tree that gives us the tree that has the highest score for each of these edges. So there were a couple questions on the on Piazza about graph-based versus transition-based, and I'd like to reiterate them here in case anybody didn't read them already. What it said in the book was transition-based. Well, what it said in the book is, I'll just put all of these up here, but it said transition-based is it allows you to design your features flexibly, but it tends to be worse on long-distance dependencies because it makes these greedy decisions. While graph-based is doing kind of global optimization. The story is a little bit different since that book was written. The last edition of the book was in 2007, and I think the new edition of the book is slight revisions of the 2007 book. But what we can say now for transition-based parsers is that they can easily condition on infinite tree context. So all of the previous decisions that you've made with regards to how you make the tree, you can remember all of them. So if you remember the stack LSTM model, it was remembering all your previous actions. It was remembering everything on the stack and what sort of trees it had, et cetera. The problem is it still has to use a greedy search algorithm, so it can cause mistakes where it basically makes a greedy decision that it then goes back to regret and says, I probably shouldn't have made this decision, but it's too late to recover from it because of the search process, et cetera. Or you can have some sort of bias in your modeling as well because you train based on these greedy decisions. And then graph-based parsing can find an exact best global solution via dynamic programming algorithms. But the disadvantage is that it has to make local independence assumptions about each of the graph edges, basically. So now more, before when the book was written, this caused a major difference between these methods, basically. Like transition-based parsers would be much better at kind of short-term things, but would fail at long-term dependencies because they'd be too eager in attaching things together. But now we have LSTMs, and LSTMs let us look at the whole sentence and kind of read the whole sentence before we start committing to decisions. So now transition-based parsers are much better. Graph-based parsers are also much better because they can kind of look at pairs of words, but in kind of an infinite context over things. So I think the difference between the two in terms of accuracy on short and long-term dependencies has reduced a whole lot. But I think still graph-based parsers tend to be a little bit better at global consistency, while transition-based parsers tend to get short-term things correct because they can condition on this local context. So the Tulio-Edmunds algorithm, just a brief summary. So we have a graph and we want to find its spanning tree. We can greedily select the best incoming edge to each node and subtract the score from each of the edges, contract, recursively call the algorithm, and expand the contracted node. And we had an example from the book where basically we have something like this. We look at the scores for all of the edges. We find the maximum score of the incoming edge to all of the nodes. So that's what the node labels indicate, 12, 7, 8. We subtract the score on the node label. So now the highest score for any of the edges is 0. And all of the other edges are negative. We then find a cycle. So the cycle on the right side, we take that and we contract that into a single node. And now we have a new weighted tree, and we can do the same thing. So basically, we now have an edge that goes into this node here, and we can see the edge going into the contracted node. We expand out the node. We can see the edge going into the contracted node is consistent with only one of the edges in this cycle. Because we can't have two heads for a single node, so we delete the extra edge that's going into flight because this edge is the one that we can't that is not consistent with the edge that was coming into this contracted node. And then you can just do this over and over and over again until you have a consistent tree. And this algorithm, basically, it's an n-cubed algorithm because each time finding all the edges is n squared, and you might have to do that recursively n times. So this algorithm can be of complexity n cubed. Is this clear? Were there any questions about this? Okay. There's other ways of doing this. This was covered briefly in the reading, but one is IceNurse algorithm. So IceNurse algorithm is entirely different from the Tulio-Edmunds algorithm. This is one for non-projective dependency trees. Non-projective dependencies were covered in the reading last time, right? So basically, Tulio-Edmunds can find trees that look something like this, where you have crossing edges. IceNurse algorithm cannot find trees like this. It can only find trees where the edges are consistent like this. And in English, projective trees are the great majority, so you might actually do better with IceNurse algorithm because it will give you this constraint of not finding things that don't look very much like English. But for another language like Czech, where there's tons of non-projective trees, you would definitely have to use something like Tulio-Edmunds. There's also Tarzan's algorithm. Actually, I don't know the correct pronunciation. That might be wrong. But there's another algorithm. It's basically a more efficient version of the Tulio-Edmunds algorithm. So the way we train these, or the way we used to train these for sure, was using the structured hinge loss objective that I talked about before. So I covered this in the structured prediction class, but basically, to say one more time, we find the highest scoring tree and penalize each of the correct edges by a margin. And if the found tree is not equal to the correct tree, we update the parameters using the hinge loss. So just a quick quiz. What if we were going to use this method for this tree? What would we have to do before running the Tulio-Edmunds algorithm? Any idea? The structured hinge loss. So when we run the Tulio Edmunds algorithm, it will find the maximal tree, and we want to make it more difficult to find the maximal tree because the structured hinge loss objective requires us to do that. So what would we do to the scores of the edges here before running the search algorithm?
Reduce them?
Yeah, and specifically which ones?
The blue ones.
Not the blue ones, but close. The correct ones, yeah. Very good. So book is the head, so we would want to reduce the score of book. Also book, probably the one from book to flight and the one from flight to that are the correct ones. So we would want to reduce the score of these edges. To instead of 12.77, make it 11.66, and that would probably result in us getting a different maximal spanning tree here, which is good because we want to penalize trees that are close, in score but incorrect. Is that clear, or any questions? Okay. So this is something that we use both in neural network land and in previous non-neural network parser land. For reference, it's worth thinking about the features that we used for graph-based parsing before neural networks came along. So what features did we use before neural nets? Basically, this is a thing of feature templates that we pasted from, or that I pasted from this rather famous paper by McDonald et al. It's basic unigram features. So we have features of the word and the part of speech tag of the parent, the word, the part of speech tag, the word, and the part of speech tag of the child, etc. Then combination features of the word and part of speech tag of the parent and child. And then also things about the surrounding words, the word and part of speech tag of the surrounding words, etc. All of these were conjoined with the arc direction and the arc distance. So this is rather important. We want to know which direction the arcs are going in and also how long the arcs are. So for arc direction, we're going to have verbs be the heads of nouns often, but we're not going to have nouns be the heads of verbs quite as often. So that's important. And then the arc distance, also we tend to like shorter dependencies in some cases, but we tend to have long distance dependencies for certain types of part of speech combinations, for example. So all of these are combined as combination features and used for parsing. Yeah. I'm sorry, I don't know what I was writing in the last one here, because they're already listed on the part of speech combination features are already listed up there. Any questions about this? Okay. Another thing that they did was they represented words with a prefix if they're long words. So if it was a long word, they would just take the first 5 letters of it. This had a function of basically turning words that had the same stem into the same thing. So this was important before. This is maybe less important now, but it's still useful considering the kind of characters within the words for training. Another interesting thing to know about is higher order dependency parsing. So higher order dependency parsing, basically I said first order dependency parsing for the example in the graph-based, and all of the edges are basically scored independently. What higher order dependency parsing does is basically instead of considering each edge independently, we consider pairs of edges for a second order parser or triplets of edges for a third order parser. So does that seem like a good thing here? Does that seem like a good idea? Anybody? Yes. Yeah, it's a good idea. So a very clear example of why this is a good idea is the right side of the second order parsing, right side of the second order parsing example. So saw with a telescope is very likely. So if we see this, if we've seen this before in our training data, then we're going to get a big bonus because seeing with the telescope is something we like to do. For third order, there are also examples that you could come up with. I don't know if seeing a girl with a telescope is something you do frequently, but maybe eating food with a fork or something like that might be something you see frequently. So you can basically kind of remember these bigrams or trigrams of dependencies in a very generalizable way to increase your parsing accuracy. So why is this not a good idea though? Lack of training data. That is true. It might overfit to our training data if we aren't very careful about regularization or only using high frequency features or something like that. There's another reason though. I got the right answer from two places at the same time. So yeah, computational complexity. This increases your computation time. So you can extract more expressive features, but it makes higher computational complexity. There are exact parsing algorithms for second order, third order. I think as I was looking for things, I realized that Max came up with a fourth order parsing algorithm like 5 years ago or something like that. So you can come up with these algorithms, but they get increasingly complex. This paper that I cited here demonstrates how you can do approximate search with higher order, and you can do basically as much, you can raise the order as much as is useful, but you have to put approximations in search. So yeah, so this is good, a good thing to do. So neural models for graph-based parsing, this is neural networks, so we have to talk about neural networks for NLP, so we have to talk about neural models. And like the transition-based parsing models that we talked about before, the first model that kind of came out in this was basically neural feature combinations. So we extract these traditional features and we let the neural network learn the feature combinations for us. And that's this paper, Pei et al. 2015. It's very similar to the transition-based model. And it's similar in even its activation function. So if you remember what I talked about last time, I talked about the Chen and Manning cube activation function, which basically let you learn feature combinations for 3 or more features. This combination function basically is cube followed by a tan H. So if you remember, the cube looked like this. The cube kind of looks like this. It increases very quickly as we get a larger scale. So the cube plus tan H basically takes the cube and then it takes the tan H. So it makes this big thing that expands really quickly, then squashes it. So we get something that looks, what does this look like? It's basically a function where we increase in the middle, maybe slower than the tan H. I don't know, actually I should have plotted this. I realize I didn't plot this before here, but it doesn't have these extreme gains after the 10H, but it can still learn the kind of like triplet feature functions that the cube one could do. And they have empirical results that shows this converges much faster and more stably than the cube function. They also use average embeddings of phrases. I'll show an example of that later. And they also use second order features. So they took the second order parsing algorithm that was used in previous parsers, and they used this as well. So what their phrase embeddings look like, basically the motivation is that words surrounding or between the head and the dependent give you important clues about whether a dependency arc is a good one or not. A very obvious example of this is a verb connects to a noun very frequently if it's the closest verb to that noun. But if you have another verb in between the verb and the noun, then probably your likelihood of connecting to that noun is going to be much smaller. So what they did here was they basically took the average of the embeddings of the prefix of the word and also the infix, which included the head and the dependent and all the words in between it, and then a few things of the suffix. And then they input all of these into their parsing model. And the results of this, do they help? So for the first order parsing and the second order parsing, basically they increased by about one labeled attachment score, and similarly for unlabeled attachment score. The speed was on par with previous graph-based dependency parsers, so it's not a huge speed gain, unlike the Chen and Manning paper, which was significantly faster. And also, interestingly, the second order neural parser was better than a third order non-neural parser. The results weren't completely comparable with the ones that I showed above, but this showed that the neural features were helping quite a bit. Are there any questions about this so far? Okay. So then the next natural thing to do in 2016 is we use a BiLSTM now, because that's what you do in 2016. So this one, basically, it just took a BiLSTM as a feature extractor for the words. It did away with all of the feature templates that were used before, and it just basically extracted features using this BiLSTM. And then you can compare. So what this indicates here is we extract the vectors from the BiLSTM. We put both of them into a multi-layer perceptron and use it to calculate a score. And then based on that, we calculate the score of our whole tree. This is also still using the structured training algorithm. So sorry, I forgot to mention this. Both this one and this one are using kind of the structured training algorithm, which means you have to decode. You decode to find the best scoring tree, and then you penalize that best scoring tree using this large margin objective. So that part is the same as the previous methods. Are there any questions about this? Probably not. It's pretty simple. So now we are on to the we're onto the kind of state-of-the-art model here. This model got the best accuracy on the universal dependencies parsing task in Connell. This is the name of the paper is bi-affine attention. I would rather call it a bi-affine classifier because it doesn't really seem like attention to me so much. It's more like they're using a classifier. But basically, their model can be summarized according to these formulas. So R here is your BiLSTM vector for word I. Rj here is your BiLSTM vector for word j, where Ri is the dependent and Rj is the head. And you run this through, you run both of these through a multi-layer perceptron. So this allows you to learn a specific representation for each word as a head or as a dependent. So basically this multi-layer perceptron can extract the important information to decide whether this word is a good head or a good dependent. And this is different depending on its role in the connection. Then what we have here is we have a large matrix of all the possible heads of each word. So this is a matrix, and we have, and then for each dependent, hi, we multiply the dependent by a matrix, then we multiply this by this matrix. And this gives us a set of scores for the words. So basically these are scores of how good a match these are as heads or dependents. The next thing down here, this is a bias basically, and this is saying given in this U2 is a parameter vector, you multiply this by all of the heads, all of the vectors of the heads, and this gives you another vector. This vector is not dependent on the current word. It's the same for all of the words in the sentence. And basically what this is saying is how likely is this word to be a head at all? Not for this particular word, but how likely is it to be a head at all? But combining these two together, you can say how good of a match is this and how good is this? The word is a head in general. And this gives you a score for each arc, basically. And you can use this to classify. This paper is a little bit difficult to parse, like not dependency parse, but for me to understand. But my understanding of the paper is that they then went to put this into a cross entropy loss that basically tried to select the best scoring head. So I don't think they're doing the structured training thing here, or at least they didn't mention it in the paper. So this is a local model, but then they have global decoding using a minimum spanning tree algorithm at the end, just to make sure that the tree that you get is consistent. And this got the best results with careful parameter tuning on the universal dependencies parsing task. I went and saw the talk about the universal dependencies parsing task, and the majority of the talk was about how they did parameter tuning. So I guess parameter tuning is very important for this model, but luckily they tell you all of the parameters they used, et cetera. So if you're interested in implementing a model like this, you can take a look. So we actually have an example of this that Max can talk about next. Are there any questions before we look at the example? Yeah.
Can you explain the last equation?
One more time, sure. So so basically, maybe I can write it on the board, but we have two parts to the equation. We have the top part and the bottom part. The top part is basically we have HI, H1, H2, H3, H4, and these are all hidden vectors of each dependent, or these are all hidden vectors for each dependent. So in dependency parsing, each word has exactly one head. Each word that's not the root has exactly one head. So we can formulate this problem as a problem of this word basically selecting its head. So what we want to do is we want to calculate a score vector for each word, and then select the maximum score as the head of that word. So the top equation is calculating the score the top part is calculating the score for each of these words, where hopefully the score of the head will be higher than all the others. The bottom part of this equation is completely independent of the original word. It's the same for all of the dependents in the, it's the same for all of the dependents in the sentence. So you can think of this as a bias vector, basically. And the bias vector will give a higher score to words that tend to be heads. So let's say you identify the main, your BiLSTM is able to identify the main verb in the sentence. The main verb in the sentence tends to have lots of children. So it should have a high score here. So it'll be like plus 3 or something like that, like some high score. On the other hand, determiners are almost never heads, right? Determiners like and the are almost always children, so they will almost never have a dependent. So based on that, if you have the, this will have a very low score, like -7, so it won't get any children. So basically what this is doing is it's just telling you how likely it is for a word to be a head. And then you add these two together, and that gives you the final score for each word, like this. Is that more clear now? Okay.
Is the age and use the by time component?
Where it's saying by affine, yes, that's the score calculation function. So you can think of it as an affine transform. So if you see hi arc dep times the matrix U plus U squared, that would be an affine transform. And they're calling it a by affine transform because you also have the thing on the left. Okay. Hopefully that's clear now. Anything else? Okay. So for another thing is probably the name of this slide should be global probabilistic training. So previously I've talked about margin-based global training and local probabilistic training. I'm sorry, actually, we had the code example that I totally forgot about while I was answering that question. So let's do the code example now. And I think we're just going to give a very brief overview of the code example because this is a little bit more involved than the previous ones, but I think it should still be useful.
Okay, so let's first go through the framework of our parser. Okay. So here is how we read the data, and we just skip this part. And from here, we first construct our model and set up the trainer. And here is the embedding size and the hidden size of the bidirectional LSTM. Then we define the bidirectional LSTM here. And the only difference is here. So when we use the bi-LSTM to extract the neural feature vectors and use them as the input of our parser. So before from this part, before this line, this is how we construct the feature vectors, and here we construct the bi-affine parser. So now we see how could we compute the decode loss. So which is the how could we turn back to the
You see the tab home?
where?
I can help. So there's a tab home up here.
Okay. Yeah. So now we see this file. This file is the class of the Bio-fan attention model, which is just the model proposed in by Stanford's Stanford parser published at this year's Aclear. So basically, it is so many parameters. So first, we need to define their linear linear transformation for their input features, and we need to distinguish their head representation and their dependent representation. And then we have their, so here, the big U is the parameters for their Bio-fan transformation, and small u is for their linear transformation. So to calculate the score, so basically the score is a matrix, is a tensor. So with their so basically we have, so if we want to compute the loss, we need to first compute the scores and then get the loss. So basically we have two loss. One is for the arc and one is for label. So pay attention here, if actually we can use one integrated score, integrated loss, but here the authors split the loss into two parts. One is for arc and one is for label. I don't know why they use this design, but it works and it achieves very good result. And here is the decoding method. So for decoding, we need to see home. Which is home? Okay. So for decoding, you need to go through this file and see the decoding algorithm, MST algorithm. So this algorithm takes the score matrix as input, and so first it just greedily search their best head for each node, and then they use their CRF algorithm. So they first find a circle in their original graph, and if there is a circle, then they construct the circle into one node and do their do the following part recursively to their MST algorithm, and then expand the circle back. So basically, this is their MST algorithm. So, yeah.
Okay. So thanks. I think that was a good short overview. I don't expect everybody understood everything from this, but now you know where to look if you want to create a graph-based parser. Are there any questions about this in general? No? Okay. I will move on. As I said, this should probably be labeled global probabilistic training. So previously we had margin-based global training and local probabilistic training. We can also come up with a local probabilistic model. Sometimes we want probabilistic models because they give us probabilities that we can use in downstream tasks as well-calibrated confidence measures. And we want something that basically looks like that, although this is from my previous slides. So there are algorithms for calculating, and in order to train a global probabilistic model, remember from the CRF class, the most important thing is to be able to calculate this partition function. We can calculate the score for the numerator easily by just stepping over all of the edges in the correct tree. But calculating this partition function is the hard part. Just so you know, in case you want to do something like this, you can use IceNurse Algorithm is a bottom-up CKY style algorithm that allows you to do it for projective dependency parsing. And you can also marginalize. Or you can also calculate the partition function. And for non-projective parsing, there is a matrix tree theorem, which allows you to compute the marginals over directed graphs. And this was applied to neural models also by Max. So from all of these lectures here, I think you now know that if you have a question, you should ask Max about dependency parsing. Cool. So that's it for dependency parsing. I'm also going to talk about phrase structure parsing as well. So phrase structure parsing, we want to calculate phrase structures that look like this. Here, it's actually an important insight here is that parsing is actually very similar to tagging. So tagging is search in a graph for the best path through the graph. Parsing is search in a hypergraph for the best tree. This also applies to dependency parsing as well, but it's especially widely used in phrase structure parsing. And I'll explain what this means in a moment. So what is a hypergraph? A hypergraph is basically similar to a graph. First, we define the degree of an edge within a tree to be equal to the number of children that something has. The degree of a hypergraph is the maximum degree of its edges. So a graph is a hypergraph of degree 1. You can see that all of the possible edges in this graph have one child, basically, one thing that the arrow is pointing to. While in the top we have 2 children for a particular edge. So what would be a hypergraph of degree 2? It's not a trick question. Yes, a binary tree. And so one thing I should note is that in algorithms for NLP, I think everybody covered the CKY algorithm, right? So the CKY algorithm is a algorithm for searching over hypergraphs of degree 2 of a specific shape. They're fully connected hypergraphs of, not fully connected, but they consider all of the connections in your grammar of degree 2. So just to give an example, if we wanted to come up with a hypergraph that encoded the ambiguity in the sentence, "I saw a girl with a telescope," there's basically 2 different common interpretations of this. One interpretation is, "I saw a girl who had a telescope." This is the blue tree, or the tree with the blue edges here. And the "I saw a girl by using a telescope" interpretation is the one with the red edge. So basically, by choosing which one of these edges is correct, we can disambiguate the parse here. So like graphs, we can add weights to the hypergraph edges. These are generally the negative log probability of finding that particular edge in the tree. It could just be a score if we wanted it to be. So we could assign a score to each of these edges. And once we do this, basically, if we search over this hypergraph, we can get something that we want, or we can do search. So the CKY algorithm, as I mentioned, is finding the highest scoring tree given a CFG grammar. So it creates a hypergraph containing all of the candidates for a binarized grammar and does search over them like this. So if you remember when Max talked about the Viterbi algorithm before, basically the score of the Viterbi, what we did during the Viterbi algorithm was we took the score of our particular edge, and then we added the score of the child of the previous state. And then we tried to find the best score of these two possible possibilities. So here we do almost exactly the same thing. The only difference is that instead of adding up a single best score for our previous state, we add up the score for all of our children. You can see here I'm only showing two different choices, the two choices that are kind of ambiguous in this sentence. So the way we would add up their scores is by taking these two equations. And then when we choose which one is the best, we would take, in this case, we're taking the minimum because a lower score is better. And we could also take the maximum if we wanted to. So this is basically exactly the same as the Viterbi algorithm, but Viterbi is over graphs, while CKY is over hypergraphs. So that, are there any questions about this? So I guess let me just put this in the same space as the CKY algorithm. I realize I probably should have had a slide like this, but basically we have, if we have a verb phrase that is going from word 1 to word 3, we have a bunch of possibilities, word 1, word 2, word 3. We could be calculating a verb and then noun. So this is one choice of an edge. We could be calculating verb past tense or verb present tense and then noun. So this would be another edge. And basically we just expand, in the CKY algorithm, we're expanding all of these edges. All of the possible edges. And then we would do a similar thing for, this would be a noun phrase over 1, 2, and 3. So we just expand all of these edges. And then take the best score. So the reason why I wanted to mention this in this framework, basically, is the connection between the Viterbi algorithm and the CKY algorithm is the Viterbi algorithm is an algorithm for searching over degree 1 hypergraphs, while the CKY algorithm is a particular algorithm for searching over degree 2 hypergraphs. So the CRF was the linear CRF that we talked about was an algorithm for calculating the partition function of a particular variety of degree 1 graphs. We can do a very similar thing that we did for the CRF algorithm to calculate the partition function using a CFG grammar. So the partition function, is the probability of the top span. So this is the exact same as CKY, except instead of taking the max, like we do in the CKY algorithm, we instead switch in a log sum exp operation. So this is the same thing we did for the CRFs that Max talked about. So if you go back and look at the CRF example, we took the Viterbi algorithm and we swapped in a log sum exp. To calculate the partition function for a tree, we take the CKY algorithm and we swap in a log sum exp. And once we have this, we have the partition function, we have the denominator of our loss function, and then we just calculate the numerator given our goal tree. And we can optimize according to that. Sorry, I realize now that I probably should have had an extra slide illustrating this, but was this, did people kind of understand, or? I see kind of yes, kind of no. But if you have questions, I'll be happy to take them either now or later. There are ways we can take this into account and train parsers that basically use a CRF over trees. So this neural CRF parsing paper, basically what it does is it has a feed-forward network that predicts the probability of a particular production rule being used at a particular span. And then it does discrete structured inference using the CKY or the inside-outside algorithm. So they have a very nice paper or a very nice diagram in their paper that demonstrates this, where basically they extract features for each span, use this to calculate the likelihood or the score of a particular rule occurring here. Then they use their normal CKY algorithm and inside-outside algorithm to basically calculate a CRF-based objective here. So this is a very elegant algorithm. It's a well-written paper, and they also have a nice examination of sparse features versus dense features or sparse features versus neural features, etc. So this is one example of kind of structured phrase structure parsing with dynamic programming. A more recent paper that came out, which is we simply tried to decide whether a span is a constituent in the tree or not. So this becomes a binary classification problem, or not binary, it's a multi-class classification problem where you have the label of each span, and then you have whether it was a constituent or not. So the idea is our our training is completely independent. We don't even worry about any CRF style training, but we just try to perform this span classification as accurately as possible. And then, we can use BiLSTM feature extractors. We can use anything we have at our disposal. And a kind of interesting thing is now this allows you to do a top-down greedy decoding algorithm as well, as opposed to the normal CKY algorithm that we use. It also allows for various loss functions, local versus structured, various inference algorithms, CKY versus top-down. Any questions about that? Okay, so I'll move on to the last one. So I spent the entire time talking about very nice ways to incorporate clever dynamic programming inference algorithms. So now I'm going to move in the exact opposite direction, which says we're going to give up on doing any clever inference or search whatsoever. And we're just going to do parse re-ranking. So we have this really nice model that you thought up. It's very well linguistically motivated, or it's great for your machine. It incorporates the best variational generative adversarial network machine learning algorithm with whatever fancy tricks you want to throw at it. But suddenly it becomes very hard to decode. It becomes very hard to actually perform search for this. So what you can do is re-ranking. So you basically generate with an easy to decode model that's pretty good. So you take state-of-the-art off-the-shelf parser and generate an n-best list or samples from the n-best list. And then you rescore it with your proposed model. And this is very flexible. It allows you to try new ideas without thinking about decoding. There's a lot of examples of models that do this and get very good accuracy. I think the first one, this was actually kind of maybe one of the predecessors to kind of, I don't know this structured inference idea, but it's basically an inside-outside recursive neural network. So the idea is you calculate in a tree structured fashion the subtree, and then you calculate also from top down. You calculate the context, and you use both of these in making your decision. And this was a pretty good paper. I realized actually I missed the original paper on recursive neural networks, which also did something like this. There's another paper on parsing as language modeling. So this paper basically they created linearized trees and just trained a big language model over these linearized trees. And the nice thing about this was they could use a large amount of kind of automatically parsed data to do this effectively. And I think for some time this had the best results on the Penn Tree Bank or something like this. And then there's also recurrent neural network grammars, which I talked about a little bit before. This is a kind of generative tree-based model that also requires re-ranking because it's very hard to generate from it. So this shows that you can kind of do very interesting things with this re-ranking framework. But there was an interesting short paper at ACL this year, which is a word of caution about re-ranking. So your re-ranking model got state-of-the-art results. This is a great thing. You're very happy. If it's a linguistically motivated model, you might think, oh, great, this validated my linguistic theory about this linguistic information being very important because now it's giving us much better results than the variational generative adversarial LSTM that the other people are using. But one thing you need to be very careful about is it might just be an effect of model combination. So model combination, I mentioned before, ensembling. Ensembling is something that always raises your accuracy. It always makes your models work better in neural land. So basically what happens is the model generating the parses can prune down the search space to a bunch of reasonable choices. And then the re-ranking model chooses the best parse only in that space. It chooses the best parse only out of the ones that the other model thought were a good idea. So basically you get ones where both of the models agree, and this is the same as ensembling, and which we already know improves our methods. And they have some interesting results here where this is the discriminative model, and they either generated candidates from the discriminative model, the generative model, or the union of the discriminative model and generative model. And then they had a scoring based on the discriminative model, the generative model, or the discriminative plus generative model averaged together. And the original paper, this is comparing to the RNN, the recurrent neural network grammars paper, which showed that basically generative models work well. And in the recurrent neural networks grammars paper, the original scores were this one, which was the baseline score, and this one, which was the discriminative parses re-ranked with the generative parses. So this looks great, right? You got a big gain of 1.2 points by introducing your nice kind of maybe linguistically motivated generative model. But then you look, they came up with an algorithm to generate more effectively from this generative model, which got better scores for the generative model. But you can see that actually the generative model got worse accuracy overall when you actually used the parses in the space found by this. So you can see that the generative model improving here was just an effect of its search space being pruned down by the discriminative model. And you actually need to be careful of that. And then you look, when you combine all of the models together, you get the best score, which is what we already know. We already know ensembling multiple models together works. So this is just one thing that you need to be careful about if you're doing re-ranking, which is that your original model might be pruning down the space. So just be aware of this. So that's all. This is all for syntactic parsing. Next time I'll be talking about semantic parsing. Are there any questions about the material today? No? Okay. If so, I will finish up here. So thanks a lot.
Quizzes are up front if you want them.